get the recording set up. Okay, now that our recording set up, let's now start talking about Vesper theory. And Vesper theory primarily concerns molecular shape. Shape and geometry. So this is really our method of rationalizing our observed molecular shapes and bond angles. So the way that this works is that Vesper theory assumes bonds are electron pairs, right? A chemical bond is a set of shared electrons, right? So when we think of, for example, a hydrogen-hydrogen bond, we have a pair of shared electrons sitting between these two hydrogen nuclei, right? That's what a bond is. And just as a refresher, what is the charge of an electron? Negative, right? So we essentially have a large amount of negative charge sitting between our two positive nuclei, okay? Electron lone pairs and electron pairs in bonds will repel each other. So for example, if we're looking at a water molecule and we have a lone pair and we have a set of bonding electrons, these sets of electrons, the lone pair electrons and our bonding electrons, they're going to repel. And why do they repel? If these electrons are both negatively charged, do like charges repel? Yes. So this is why you end up with this repulsive interaction in, for example, a water molecule. And due to this repulsive interaction between the bonding electrons and the lone pair electrons, you end up with changes in your molecular shape. Okay, so electrons in bonds and lone pairs are arranged to minimize these electron-electron repulsions. So we're trying to get all of our electrons as far apart from each other as possible, following, of course, orbital limits and bond length limits. So the geometry of a molecule depends on two things: the number of atoms bonded to the central atom, in other words, the number of sigma or single bonds, if we're thinking about it from the perspective of valence bond theory, and the number of lone pairs around a central atom. So those are the two things that we are going to count: atoms bonded to our central atom and the lone pairs around our central atom. Now, we classify each of these two functional motifs as an electron group or a charged sphere. So for the purposes of Vesper theory, we're going to be counting each single lone pair of electrons and each bonded atom. So we're counting lone pairs and bonded atoms. So the key feature of this model is that a bonded atom is one electron group, regardless of if it's single, double, or a triple bond. And the way this can be rationalized a little bit is that if you think about, for example, a carbon-nitrogen triple bond. Fundamentally, if we break apart this triple bond into its component bonds, what three types of bonds make up a triple bond? One sigma, yep. And 2 pi, yep, exactly right. So when we're thinking about electron-electron repulsions, even though there are substantially more electrons in this triple bond, are all of our electrons still localized between carbon and nitrogen? Are electrons primarily just sitting between these two atoms? Yes. So from the perspective of electron-electron repulsions, we're primarily concerned with regions where electron density is located, and that's mainly bonds, be it single, double, or triple. No matter if we have more electron density in this triple bond, it still has a similar repulsive interaction to the electrons found in a single bond, for example. So we can coin the total number of electron groups or charged spheres via the steric number, which is abbreviated as Sn. It's the total number of bonded atoms plus the total number of lone pairs around a single atom. So a steric number is calculated for each atom. Okay, so what we're going to use is there's a direct correlation between the steric number and what's known as the electron pair geometry. Now, the distinction between electron pair geometry and molecular geometry is that this electron pair geometry does not account for lone pair repulsion. So this gives you, the electron pair geometry is reflective of the rough molecular shape. Okay, so let's look at a few examples, and let's start to look at electron pair geometry. So these are not molecular geometries, these are the simplified electron pair geometries. These are the rough shapes of our molecules. So let's start off with the simplest, and that's the linear geometry. We have two sources of electron density or charge spheres, and geometrically, if we have a circle, for example, and we have 2 points on that circle. So let's draw out our 2 points in a different color. So let's suppose we have 2 points on this circle. And these are going to be our regions of electron density that we're going to call our bonds. So these are our bonds surrounding our central atom. Now, my question to all of you is, and one thing that I'd like us all to consider, if we have these bonds around our central atom, what is the farthest angle that we can separate these regions of electron density, that we can separate these bonds by? 180 degrees, right? We take 360 divided by 2, and that gives us a 180 degree bond angle. So you can use the geometric proof in this case. So the bond angle for the linear electron pair geometry is 180 degrees. So a few examples of molecules with linear electron pair geometries are beryllium dichloride, or BeCl2, and carbon dioxide, which is CO2. Now, if we're being really attentive, when we discussed hybridization, were we also able to correlate hybridization with molecular shape and bond angles? What hybridization best corresponds to the linear electron pair geometry? SP. Yep. So when you think linear, I want you to think SP hybridization. And really, I want you to think about hybridization from the perspective of the geometry of our molecule determines what hybridization we assign to each atom. Geometry informs hybridization. Okay, now for carbon dioxide, or CO2, let's really highlight the charge sphere counting. So how many charge spheres are around our central carbon atom? 2. The double bonds are just counted as 1 charge sphere. 1, 2. Always make sure to keep that in mind. And this matches our model with hybridization, where we count sigma bonds to determine the amount of hybrid orbitals we generate. Okay, let's now move to the next major hybridization. Let's move on to the next major electron pair geometry and the next major hybridization scheme. What makes a molecule trigonal planar? So again, we're talking about electron pair geometry. We have 3 sources of electron density or charge spheres. And again, via the geometric proof, if we draw a circle and we draw out our 3 bonds, let's draw out our 3 bonds. 1, 2, 3. So we have our 3 sources of electron density, and then we have our central atom. Let's pick aluminum for our central atom in this case. What is the farthest we can separate our bonds? What's the farthest angle we can separate our bonds? 120. 360 divided by 3 gives us 120 degrees. So when we have a trigonal planar electron pair geometry, our bond angles are 120 degrees. Now, examples of molecules with the trigonal planar geometry would be BF3. Another interesting example, just to showcase molecules with a trigonal planar geometry, would be nitrate, which is NO3 minus. Now, one unique quirk of NO3 minus, how many charge spheres again are around our central nitrogen? 3, because remember we count this double bond as just one charge sphere. Okay, now if we wanted to correlate this electron pair geometry with a hybridization, what hybridization best matches this 120-degree bond angle and 3 substituents? sp2. So when you think trigonal planar, I want you to think sp2. And again, as its name implies, just reading off, planar, what does that mean? 3D shape or flat? Flat. They're completely flat. So when you see sp2 and sp, I also want you to think flat molecules. These are quote unquote flat. There's no real three-dimensional space here. It's all in the 2D plane. Okay, our last major electron pair geometry that we're going to discuss is the tetrahedral geometry. So let's discuss the tetrahedral geometry next. For the tetrahedral electron pair geometry, we have 4 charged spheres. Now, when we have 4 charged spheres, so 4 bonds, 4 single bonds or lone pairs, it becomes optimal to arrange our molecule in 3D space. Now, you can prove this geometrically, but the optimal bond angle to separate all of our bonded atoms is 109.5 degrees. It's as if each of our bonded atoms is a corner on a tetrahedron. So that's where the tetrahedral name is derived. And a classic molecule with a tetrahedral electron pair geometry would be methane, CH4. You'll often see this dash wedge notation utilized when we discuss tetrahedral molecules because we're starting to appreciate the fact that these electron pair geometries adopt 3D shape. They're not just flat in the 2D plane. They have 3-dimensional shape. And that's often reflective, and it's going to be really critical when we start to discuss what's known as stereochemistry, or how are atoms arranged in space. Now, what hybridization does this 109.5 degree bond angle best correlate with? What hybridization involves 4 bonded substituents and sp3? Exactly right. So we have correlated effectively hybridization and electron pair geometry. Does that make sense to everyone? Okay, so what we're going to do next is we're going to practice drawing some Lewis structures, and I want you to tell me the electron pair geometry. This is the rough shape of our molecules. And I'll start us off with AlCl3. So doing some counting, aluminum contributes 3, chlorine contributes 7, and we have 3 chlorine atoms to work with. That gives us a grand total of 24. What is our central atom going to be? What's the least electronegative non-hydrogen atom? Aluminum, exactly right. Okay, and we're gonna, oh, one moment. Okay, and we're gonna surround it with our 3 chlorine atoms. Let's now switch to a different pen color, and let's account for the fact that we formed 3 bonds. So how many electrons did we use? 6. So we have 18 remaining. Each of these chlorine atoms need how many additional electrons? 6. Okay. So we're going to burn through 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons, and we're done. We've used up all of our electrons. Is the octet rule fulfilled? No. Does it have to be? No. Because as we discussed, aluminum is what's known as an incomplete octet structure. It's a Lewis acid. It only needs to form 3 bonds. If we formed a 4th bond, we would be violating formal charge rules. Does that make sense to everyone? If you're wanting a review on that, please look up the section titled Incomplete Octet Structures. So let's now look at the 3D molecular shape. Let's do a 3D drawing. And let's really try to appreciate the molecular shape of this molecule. So we have AlCl3, and as you've noticed when I'm drawing a lot of these Lewis structures, I'm subconsciously already arranging my bonds with the correct bond angle. Because what is our bond angle for aluminum trichloride if we have 3 charged spheres? 120. So I really encourage you when you draw your Lewis structures to start to think about your electron pair geometry and draw your bonds spaced out appropriately so that they reflect the actual bond angles. And as we discussed, this electron pair geometry, if we have 3 charged spheres, is what? So sp2 is the hybridization, but the actual electron pair geometry is trigonal planar. Perfect, perfect. So what I'd want you to do now is to tackle this second example. I'd like you to draw a valid Lewis structure, and I really want you, when you draw your 3D molecular drawing, to have your drawing reflect the actual shape of your molecule. Yes?
So back up to the example of methane.
Yes.
With the stripe bond and the triangular bond, which one of those is considered popping out? Which one
The wedge is going out of the page towards us, so it would be this carbon right in the front, and the dash is going into the page, which is the carbon in the back. We'll talk more about dash wedge notation later in the stereochemistry chapter. The main thing I want you to appreciate for now is that each of our hydrogen atoms are separated with a 109.5 degree bond angle, and it's arranged almost like a tripod with 3 legs and then 1 atom on the top. And I'll be walking around to check to see how everyone's doing. Everything going okay? Yeah, looks good. Everything going okay? Yeah, looks good. Perfect. So everyone's quite fast at this. So let's talk a little bit about the logic. So counting electrons, carbon contributes 4, hydrogen contributes 1, chlorine contributes 7, and we have 3 of them. Adding up our electrons, we have 26 electrons to work with. And what do we choose for our central atom? Carbon, yep. We then surround it with our 4 other atoms, and we form 1 bond each. Perfect. So far, so good. Based on the fact that we've now formed 1 bond each, how many electrons have we used up? 4 bonds, how many electrons is that? 8. So we've used up 8 electrons. We now have 18 electrons remaining. How many electrons do each of these chlorines need? 6. So we use up 2, 4, 6, 8, 10, 12, 14, 16, 18. And we're done. So these are relatively easy Lewis structures, but the goal is to start to appreciate the molecular geometry. So as we have 4 charged spheres, what electron pair geometry do we have? So the hybridization is sp3, but we call the geometry tetrahedral. Okay, so to reflect that, we're going to draw out our central carbon atom. We're going to draw our bond angles to reflect the fact we have a 109.5 degree bond angle. And then because the central carbon is tetrahedral, we're going to indicate it has 3D shape by using dash wedge notation. So we put one of our substituents with a dash and the other with a wedge. And what this is essentially showing, and I've drawn this a little bit more suggestively here, is that the chlorine with a wedge is pointing out towards us, and the chlorine with a dash is pointing away from us. Does that make sense? Okay. So what we're now going to talk about is how the lone pairs affect our overall molecular geometry. For now, we've been talking about electron pair geometry, which is a rough estimate of molecular shape. We're now going to go into a bit more of a finer detail and talk about distortions in bond angles. So let's talk a little bit about lone pairs, as they're critical to understanding the difference between electron pair and molecular geometry. So electron pair geometry is just based on charged spheres. We don't care whether or not the charged sphere is a bond or lone pair. In molecular geometry, we are accounting for lone pair and bonding electron repulsions. And molecular geometry depends on our electron pair geometry and the number of lone pairs. So in this case, we're going to pay special attention to the number of lone pairs. Now you may be asking, why do we care about lone pairs? Well, when we think about a non-bonding pair or a lone pair, these lone pairs overall take up more space as a result of the fact that with our lone pair, we have these two electrons jammed together into a really tiny space, and these electrons are going to want to repel and occupy as large of a region of space as possible. That means these lone pairs are space hogs, and they're going to take up a ton of space and push away our bonds, distorting our geometry. So, in general, electron lone pairs repel our bonding electrons, leading to a smaller bond angle. So, for example, in ammonia, does everyone notice this very conspicuous lone pair? Comparing our ideal tetrahedral bond angle of 109.5, is our bond angle for ammonia smaller or larger? Smaller. And as a general rule, you lose about 1.5 degrees per lone pair. For your tetrahedral, and then approximately 4 degrees per lone pair for your trigonal planar. You don't need to know the exact bond angles for each of these molecular geometries, but what I do want you to appreciate is if you see a bond angle that does not match our ideal geometry, you should be able to explain why. Does that make sense? Okay. Any questions on this scheme? Yes.
So it's the smaller angle on one side of the molecule, then isn't it going to be a little bit larger on the other?
Yes, and the larger angle is the angle separating the lone pair and each of our bonds. So essentially all of our bond angles decrease because we can't measure the angle between this hydrogen and this lone pair. You can only measure the angle between bonded atoms. Does that make sense? So that's why all of the bond angles decrease, because the distance between our bonds and this lone pair has increased. Let's now talk about each of our molecular geometries, and there aren't a lot of them. Since thankfully, when we're in the realm of organic chemistry, you're going to see primarily tetrahedral and trigonal planar derivatives. So let's talk about the trigonal pyramidal geometry. So first and foremost, this occurs when we have 4 charged spheres or a tetrahedral electron pair geometry. So think about it, we have our electron pair geometry, and then we have our molecular geometry. So electron pair is general, molecular geometry is specific. So in this case, when we have 3 bonds and 1 lone pair, that gives us the trigonal pyramidal geometry. The key feature of this molecular geometry is that we have a 107.5 degree bond angle. The poster child for this geometry is ammonia, which is NH3. And I'm going to draw the lone pair just to show the fact as to why ammonia adopts a trigonal pyramidal geometry. Does that make sense to everyone? Now, if we really start to pile on the lone pairs, we end up with what's known as the bent molecular geometry. So the bent molecular geometry is a derivative. It has 4 charged spheres, and it's a derivative of the tetrahedral electron pair geometry. So the electron pair geometry is like our giant umbrella. It's the general shape. The molecular geometry is more specific. When we have 2 bonds and 2 lone pairs, we have the bent molecular geometry. And the bond angle, if we add another lone pair, would we expect our bond angle to increase or decrease? Decrease. So it's even smaller, 105.5 degrees. The picture has it 104.5. Different textbooks will take off different degrees for lone pairs, and there's some variation in textbooks. Yes.
Which one are you expecting us to know?
I just want you to know that it's the smallest of all the tetrahedral bond angles. So if you put anywhere between 104 to 105, that's perfectly fine. The main thing qualitatively is that the bond angle is smaller as a result of these lone pair repulsions. And that's the key point that we're going to apply in more complicated systems. Any questions so far? These are the 2 molecular geometries from the tetrahedral superclass. If we don't have any other questions, let's now talk about our derivatives for our trigonal planar geometry. So what makes a molecule bent for the trigonal planar geometry? So we call this bent, in parentheses, trigonal planar. So in this case, it's a derivative, of course, of the trigonal planar electron pair geometry, where we have 3 charged spheres. And in this molecular geometry, we have 2 bonds and 1 lone pair. And this lone pair has a dramatic effect on our bond angles, leading to a 116 degree bond angle. Anytime you have a lone pair, it pushes our bonds closer together, leading to a distorted bond angle. Now, you may wonder, why don't I have any variations of the linear geometry? Why am I not showing you bond angles for derivatives of the linear geometry? It only has 2 bonds, right? If we replace one with a lone pair, we can't report bond angles, right? You need multiple bonded atoms. Okay, as a summary table, here are all of the common electron pair and molecular geometries that you'll see in this class. This is not comprehensive. There are some expanded octet geometries associated with sulfur and phosphorus. We'll address those as they come up on an as-needed basis. If you want to review this, I would look at the Chapter 10 101 review slides. Any questions on molecular geometry and electron pair geometry? Yes?
You said for reference it was Chapter 10?
Yes. So let's put this into practice now. There's really no use in talking about something without practicing it. So I'll do the first example. And all of these structures you will see again. These aren't just random structures for practice. These are ones that you'll be drawing a lot in this class. So the first of which is CH2CO. And no, this is not a typo. This is a very interesting structure. So first things first, each of our carbons contributes 4 electrons, hydrogens contribute 1, and our oxygen contributes 6. So adding up our total, we have a total of 16 electrons to work with. And for this structure, I'm going to use the condensed method. So I'm going to write each of my motifs as our formula has them. So from left to right, what's the first thing I'm going to write? Yep, CH2. So I'm going to write a carbon bonded to 2 hydrogens. And what is attached to that? What's the next motif? Carbon, okay. And then what is attached to that carbon? Oxygen. Okay. This is an interesting intermediate known as ketene. We're not quite done yet. So let's now subtract our bonding electrons, 2, 4, 6, 8. So we've used up 8 electrons. We have 8 electrons remaining. Now, if we want to complete the octet of all atoms involved, where do we put our lone pairs? If this middle carbon is central, we're going to start with oxygen. So oxygen needs how many? 6. Yep. 2, 4, 6. We have 2 electrons remaining. What's our other outer atom? The carbon with the 2 hydrogens. Yep. So let's put a lone pair on this outer carbon. Now, does the central carbon have a complete octet? No. So let's convert one of these bonds, or one of these lone pairs, into a double or triple bond. Now, just as a side note, why did we start with the lone pair on this carbon, theoretically? Is it favorable? Oh, yes. Exactly right. So we want to minimize negative formal charges on this carbon. Okay, do we have a complete octet at this point? No. So let's form another double bond. Okay, perfect. So now we have a complete Lewis structure that fulfills the octet rule. Now we're going to dissect this, and let's look at each molecular geometry. So first and foremost, let's look at this bottom carbon. What is the molecular geometry of this bottom carbon? With how many charge spheres? 3. So what's the geometry? Yep, trigonal planar. Okay, what about this central carbon? How many charge spheres does this central carbon have? 2. So what's its molecular geometry? Linear. And as a key point here, the molecular geometry and the electron pair geometry only match if we have 0 lone pairs on each of our central atoms, which is the case in this example. So, to respect our bond angles, as I've already done, so surrounding our central carbon on the bottom, what is this bond angle? If it's trigonal planar, what's the bond angle? 120. Okay. And what is the bond angle surrounding the upper carbon in ketene? 180. As an exercise for you to consider, try to think how this would look in a valence bond picture. These structures are particularly reactive and unstable as a result of bonding interactions that you'll see in its valence bond structure. So, with this established, any questions on this example before I let you loose on an example of your own? Okay, if there are no other questions, let's let you loose on the following 2 examples. So let's zoom in so that way we can see it. And I'd like you to write valid Lewis structures for each of the 2 examples and assign the molecular geometry, not electron pair, molecular. Any questions? Everything going okay? Okay. Everything going okay? Okay. Any questions? Okay. Any questions? questions? Looks good so far. Any questions? Okay. Any questions? Well, in general, you want to attach hydrogens to more electronegative atoms. So on the right, the hydrogen should probably be on oxygen. Any questions? Okay. Any questions?
I think I'm good. And you said for the angles,
Wait, how many questions do you have there?
just the thin rays.
Oh, okay.
Yeah.
Yep, that looks good.
So
Mhm.
we want to attach it to a more electronegative first.
Yep. Mhm. In general, hydrogen is attached to more electronegative atoms first. Yeah. So. Everything going okay? Looks good so far. Everything going okay? Yeah, looks good. Only needs one minor change and then it's complete. Yeah, looks good. And try drawing the bond angles, but your assignments are correct. So to help everyone along in this process, for this first example, I saw a lot of reasonable solutions. So let's now move to discuss this as a group. So counting up our electrons, each carbon contributes 4 electrons, and we of course have 2 carbons. Each hydrogen contributes 1 electron, and we have 4 hydrogens. And each oxygen contributes 6 electrons, and we have 2 oxygens. So then, adding up our total, we have a total of 24 electrons to work with. Now, I'm going to utilize the condensed structure method. So what's the first motif I'm going to draw? CH3. So I'm going to draw a carbon with 3 hydrogens attached to it. The next motif I'm going to draw, from falling from left to right, what's attached? A carbon, yep. And that carbon has 2 oxygens attached. And when we're deciding where to place our hydrogen, in general, hydrogen is placed on the more electronegative atoms preferentially. So it's going to be attached to one of the oxygens. If you're been reading ahead and thinking about functional groups, this CO2H is a common arrangement of bonded atoms known as a carboxylic acid. But we'll handle this from scratch just to see how this works. Now, counting our bonds, we have 1, 2, 3, 4, 5, 6, 7 bonds. So we have used up a total of 14 electrons. We have 10 remaining. Where do we place those 10 electrons? Where do we place them? Oxygen, yep. The first one needs 2, 4, 6 electrons. The second oxygen needs 8, 10. Perfect. So we've used up all 10 of our electrons. And my question to all of you is, how do we finish the octet on carbon? Yep, we form a double bond. So we move our lone pair down and we form a double bond. Now, I've subconsciously moved the top oxygen lone pair. Why? Yes. Yes, we want to minimize formal charges. And an oxygen with 2 bonds and 2 lone pairs has a formal charge of 0. So we're now ready to assign geometries. So looking at the leftmost carbon, what is the geometry? Tetrahedral. Has 4 bonded atoms, 4 charged spheres, 0 lone pairs, so it is tetrahedral. This second carbon with 3 charged spheres and 0 lone pairs is what? Trigonal planar, which I abbreviate as trig planar. Finally, this rightmost oxygen with two bonds and two sets of lone pairs adopts what geometry? Bent. Interestingly, and what I want you to write in your notes is I want you to put a little asterisk next to this bent geometry, because the bond angles associated around that oxygen are not quite that of a typical bent tetrahedral geometry. And we'll talk about why that is in the resonance chapter. Okay, let's look at one more example. This time I'm going to draw it using a functional group method. So we have NH2CO NH2. I love these types of molecules because they're perfectly symmetrical. If we're counting electrons, nitrogen contributes 5. We have 2 of them. Hydrogen contributes 1 electron, and we have 4 of them. Carbon contributes 4, and oxygen contributes 6. If we add up our total, we end up with a total of 24 electrons to work with. And again, we'll use the condensed structure method. So what's the first functionality that I'm going to draw in my molecule? NH2. So a nitrogen with 2 hydrogens attached. Attached to that nitrogen is what? Carbon. And what is attached to that carbon? Oxygen. And what else is also attached to that carbon? Yep, an NH2 functionality. This CO is another textbook functional group. It's known as a carbonyl functional group. And in this case, it's part of an amide functionality. That's not important for now. What is important, we now have our skeleton and we can count the electrons that we've used. 2, 4, 6, 8, 10, 12, 14. We have 10 electrons remaining. Let's now place our electrons as lone pairs. Where do we place them first? Technically oxygen first and then nitrogen, but both are fine starting points. So we place 6 on oxygen, and how many electrons do we place on each nitrogen? 2. Perfect. So we have now fulfilled the octet rule for all of our atoms except for carbon. And how do we remedy this? Double bond between what atom? Oxygen, yes. And what is our motivation behind choosing oxygen's lone pair? Formal charges. Yeah, we want to minimize formal charges. So both of these nitrogens are equivalent. And what is their expected geometry? Just Trigonal Pyramidal. Yes, that would be just looking at it at face value. And again, I want you to put a little asterisk. And in this case, it's quite pronounced. If you're curious what the actual geometry is, and this would be an interesting thing to look into for your reading, the actual geometry is trigonal planar. And I want you to think and try to figure out, why is that? And I would encourage you to look at the chapter on resonance as pre-reading. Sticking to some more standard geometries to really ensure that we're practicing. What is the geometry around this central carbon with 3 charged spheres? What's the geometry? Yep, trigonal planar. Does that make sense to everyone? Yes.
So I was a little bit confused why. So when you draw the structure, you attach the carbon to the nitrogen. Is that for like them to be symmetrical? It's
not just for symmetry, but it's also just the fact, in general, it's rare for you to string together multiple electron and negative atoms bonded to each other.
Okay.
One, because their bonds are very weak. They're not particularly stable bonds, and those bonding motifs typically are found in very unstable molecules. Yeah. Does that make sense to everyone? Yes.
And so the geometries for the nitrogen, the Trigonal Pyramidal, and that's due to the lone pairs.
Yes, but the just looking at face value, we would expect it to be trigonal pyramidal. In reality, it's trigonal planar. And that has to do with, and I'll use a separate color for this, has to do with the fact that we can draw a resonance structure where nitrogen only has 3 bonded atoms and 0 lone pairs. And we'll talk more about how resonance has a dramatic effect on geometry in later chapters. Does that make sense to everyone? So until we cover resonance, you can take these structures at face value. The moment we cover resonance, you're going to have to appreciate the effect of resonance on geometry. Does that make sense to everyone? Okay. So, any other questions on these examples? You always want to be thinking about molecular shape because it helps us understand properties and reactivity. So, with that, let's continue on. One question that students often have with many of these examples, did you not have the exact same structure that your instructor wrote? That's normal. There are many valid structures you can draw for the same formula. And we call structures with the same formula, but with a different arrangement or connectivity of our bonded atoms, constitutional isomers. So, for example, CH3CN has multiple plausible Lewis structures for each constitutional isomer. Now, if we're just using the functional group method, we can draw the first major Lewis structure for CH3CN. This CN arrangement and the CN arrangement of bonded atoms is known as a nitrile functional group, which we'll talk about in more detail in a moment. So this is one of our valid structures for CH3CN. It is not the only valid structure. The very smelly counterpart that thankfully we don't have students handle is what's known as an isonitrile. And although this switch may seem very mild-mannered, oh, one moment, sorry. Although this switch may seem very mild-mannered, this isonitrile will probably scare all of us out of a building if it was ever let loose due to its horrific smell. Acetonitrile, which is CH3CN, is perfectly harmless. Does everyone notice how the arrangement of bonded atoms has changed? How the connectivity has changed? That is critical when we discuss constitutional isomers. There are a few other potential constitutional isomers that are a little more esoteric, but I'll draw one of them here. This is an amine variant of ketene. Does everyone notice how it looks very similar to the structure for ketene that we drew earlier on in this class? Now, there's another type of isomer that we need to discuss that are often drawn in organic chemistry, and the main place that we see it in the introductory chemistry courses has to do with compounds containing double bonds. So let's talk next about the other type of isomer, which occurs when we have structures with the same formula and atoms are bonded with the same connectivity. Wow, these molecules are very similar. However, they have one critical distinction that biological systems can pick up on, that chemical reagents can pick up on, and it's the fact that these isomers with different 3D shape are known as stereoisomers. So a key example of this is for the formula Br2C2H2. Now, for this structure, we can draw both constitutional and stereoisomers. So let's showcase that. So if I was writing out my starting point and drawing a Lewis structure from scratch, I could end up with this as my first Lewis structure. Now, to talk about a wonderful trick for drawing constitutional isomers, and this is pretty easy, all you have to do is put a box around two of your functional groups or two of your substituents on different carbons. And all you have to do is swap their positions. Okay? So if I switch this bromine and this hydrogen, I can generate a new connectivity of atoms. So these two structures are constitutional isomers. Because is our connectivity of atoms the same? Are the same atoms bonded in the same arrangement?
Oh, no.
No, they're different, right? This carbon in this structure has two bromines. This carbon in the second structure only has one. So the connectivity of our atoms is different. Another structure that you can draw, which is an example of a stereoisomer, same connectivity, different shapes, has to do with how our substituents, how our bromines are arranged about our double bond. In the first structure, they're on the opposite side of the double bond, and we call these trans. In the second stereoisomer, we'll draw our bromines on the same side of the double bond that we would call cis. Now, as we can see, does each carbon have the same connectivity? Does it have the same atoms attached to it? Yes. But looking clearly at their 3D shapes, considering bromines are huge, do these molecules have the same shape? Same or different? Different, yep. And we call these two isomers stereoisomers. Same connectivity, different 3D shape. And stereoisomers is the main focus of chapter 4. Whoops. So if you're interested in reading more on that, that's a good place to start. Any questions on constitutional and stereoisomers? Okay, if we don't have any other questions, let's continue on. Let's continue on. One moment. Okay, so let's now make sure, and really have to be careful about this. You want to make sure your constitutional isomers have a different bond connectivity. For example, let's take a look at the following 3 molecules. They're all of the formula C4H10O. So all of these structures have the same formula. They have 4 carbons, 10 hydrogens, 1 oxygen. Okay, so we've crossed our first hurdle. Now, looking at all of these structures, if we compare structure number 1 and structure number 2, do they have a different connectivity of atoms? Is each carbon atom bonded to a different set of other atoms? Yes, so these two are definitely constitutional isomers. Okay. Let's now take a look at structure 2 and 3. And for that, I'm going to change colors to a red pen because this is an interesting example. If we compare structure number 2 and structure number 3, do these two structures have the same or different connectivity? Same. So are these constitutional isomers? No. So these are not. So our answer would be number 1 and number 2 are constitutional isomers. you can also say number 1 and number 3 are also constitutional isomers, right? Because if we compare 1 and 3, do they also have different connectivity? Yeah. It's a bit of a redundant statement, right? Because are 2 and 3 the same or different? They're the same. They're exactly the same connectivity. Exactly the same arrangement of atoms. The only thing I did, if you notice, is just rotated my molecule. So they're exactly the same. So what I want everyone to do now is I'd want you to draw at least 2 constitutional isomers for the following formulas: C3H5NO2. So you're going to utilize your skills drawing Lewis structures, and you're going to try to come up with 2 different valid Lewis structures. So make sure you're following the formal charge and octet rules whenever possible. And I want you to come up with 2 valid structures for this. Any questions? Any questions? Any questions? Okay. Any questions? Any questions? Okay. And I would recommend starting from scratch on the first one and then try moving your substituents around. Any questions? Okay. Any questions? Okay. Everything going okay? Yeah, let's do it. And NO2 is a function. Think of it like a package. NO2, those atoms are going to stick together. And since you made the structures. Yes. Yep. 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 You're definitely on the right track. Any questions? Everything going okay? Looks good so far. The only thing is you want to make sure you're following the octet rule. So try counting electrons and filling in the remainder from there. But the skeleton's perfect. Everything going okay? Let me see. Looks. I won't say it's wrong necessarily, but it needs to be modified slightly. Because you still have 2 other hydrogen atoms. So just like when we're drawing octets, only form those double and triple bonds when you need. Yeah. Yeah, I forgot. It's okay. It's okay. Everything going okay? Yeah, that rough skeleton looked good. You just need to make sure the octet rule is fulfilled and all of your atoms have a complete octet. Yep. I couldn't quite happy yet. Just kind of moving things around. So I saw a lot of reasonable answers so far, and I really encourage you, the main skill you want to develop quickly in this class is looking at a formula and being able to quickly write out a Lewis structure. So I'm going to follow the packaging approach. So C3H5. So that tells me I'm going to draw 3 carbons attached to each other, and I have 5 hydrogens to work with. Okay? So I'm going to start from left to right. So I'm going to put my 3 hydrogens on my leftmost carbon. And now, considering I have 2 hydrogens remaining, and both these carbons need a complete octet, I'm going to start by placing each of my hydrogens on one carbon each. This is purely arbitrary decision making. I'm just vocalizing my thought process here. Okay, so I've used up all of my hydrogens, and then attached to this carbon, I'm going to put this nitrogen with 2 oxygens attached. This is another functional group known as a nitro group. So the quicker you can recognize functional groups, the more you can save time in writing out Lewis structures. So I'm going to have a nitrogen with 2 oxygens attached. So this is my skeleton. Now I'm going to count electrons to fill in my skeleton. Carbon contributes 4, and we have 3 carbons. Hydrogen contributes 1, we have 5 hydrogens. Nitrogen contributes 5, oxygen contributes 6, and we have 2 of them. So 17, 22, 34. We have 34 electrons to work with. We have formed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds. So we've used up how many electrons? 20. Yep. So we have a total of 14 electrons remaining. Perfect. Did I make a math error? No? Okay. So now with these 14 electrons, where are we going to place the lone pairs first? Oxygen first, because it's most electronegative. So we're going to use up 12 of our electrons. We have 2 electrons remaining. Now, and you can attempt to place the lone pair on nitrogen. That is not inherently wrong. However, the nitro group has a very specific bonding pattern that looks a little bit like this. So using our knowledge of this functional group, we can eliminate a decision-making step. You can draw a valid structure with a lone pair on this nitrogen, but it requires a little more tuning and moving atoms around. Now, what other atom does not have a complete octet that needs a lone pair to complete its octet? Carbon, yeah. So let's pick one of these carbons and let's add a lone pair. So we're out of electrons. So our next step to fulfill the octet rule and minimize formal charges is to do what? Form a double bond. Exactly. Let's take this lone pair and let's use it to form a double bond. So now we have a structure that fulfills the octet rule. Of course, your structure may be different. Your structure can still be correct as long as it follows the octet rule and minimizes formal charges. Now, to showcase how we can get, how we can produce constitutional isomers, probably the easiest way is to identify a substituent and then swap it with hydrogen. So remember our bromine example, right? When we swapped bromine and a hydrogen in our double bond. Now there are 2 ways of thinking about this. Either you can swap this carbon and this hydrogen, or alternatively, what would an equally valid method be? You can swap this hydrogen and this entire nitro group. The fastest way to draw constitutional isomers is to switch the positions of a functional group, be it a carbon or other more complicated functional groups such as this nitro group, and a hydrogen. Just don't swap both of them, because then you'll be right back where you started. Okay, so let's pretend that we're swapping in red, we're performing a swap in red. And that gives us the following structure after the swap. So then, in this structure, do we have a different connectivity of atoms? Is the connectivity between atoms the same or different in these 2 structures? Different. And the reason why I like this method of swapping a group and hydrogen is I don't have to go and mess with the other portions of my structure. It's just a nice, clean one-to-one swap. Does that make sense to everyone? There are other ways, of course, you can just start from scratch every single time and change your arrangement of atoms, change what central atom you have. There are other equally valid Lewis structures you draw. Actually, for this one, there are at least, I'd say at least 5 or 6. As long as you're following the octet rule and obeying formal charges, it's a perfectly fine answer. This is part of the reason why we love condensed formulas. Because otherwise, if I just gave you this chemical formula, it's ambiguous. It could be any of these structures. So condensed formulas really help reduce ambiguity. Yes? Yes. Oh, if you swap these two directly? So that is not an incorrect logical approach. However, if you do swap these two, you've essentially rotated your molecule. Oh. These two?
Yeah.
I can draw it. One moment. Is it okay if I erase this structure to showcase option number B or option B? Let me erase. So in the case that you do swap the nitro group and the hydrogen, let's showcase that structure. So we have a carbon with a CH3 group attached. Okay. Attached to this carbon, which has a double bond, is a nitro group. Whoops, one moment. Okay, and then we have our 2 hydrogens. In fact, you get the same structure whether you swap the methyl and this hydrogen, the CH3 group, or whether you swap the nitro group and this hydrogen. Does that make sense? So we've actually generated the exact same structure as from the previous swap. Any other questions on drawing constitutional isomers? Let's check. We have plenty of time. It's great. That clock's 5 minutes fast. So we're going to continue on, and we're going to talk about tricks to draw Lewis structures quickly. And this involves, yes.
This changes actually what it is, though, like kind of what you were saying.
Yes, it's an entirely different compound with entirely different properties and reactivity. Constitutional isomers are distinct chemical species. Does that make sense? Perfect. So, to draw constitutional isomers quickly, I just want to remind everyone of the fact that we have tables upon tables of bonding preferences for each atom, for each formal charge. So we can utilize these bonding preferences to quickly string together our atoms, right? Because it tells us, for example, if we have a neutral carbon, we're going to need it to have 4 bonds. These are our single bonded preferences. We can also draw bonding motifs for double and triple bonded structures. You don't need to memorize these, but I'd just like you to acknowledge their presence and try practicing using these motifs and recognizing these motifs as you draw Lewis structures. Because as you'll notice, the more and more you draw Lewis structures, the more you'll be able to quickly draw out atoms connected together using these motifs. Okay, now we also know that most organic compounds are represented using condensed structures and condensed formulas. And from the condensed formula, the arrangement of atoms can be determined. For example, in CH3CN, we are able to establish that we have a carbon connected to 3 hydrogens. That carbon is connected to a second carbon, which is connected to a nitrogen. Now, to tie this all together, because this is a neutral molecule And considering that we have a nitrogen atom at play, one of the common bonding motifs to fulfill the octet rule involves having a nitrogen with a triple bond and a lone pair, which is shown right here. So acknowledging these bonding motifs can help us quickly arrive to the conclusion and reach proper Lewis structures quickly. This is often how chemists informally draw these structures efficiently. Does that make sense? Now, there's an even more powerful method that involves leveraging condensed formulas and the idea of functional groups. So, before we get to functional groups, we just really want to make sure we understand how condensed structures function. There are two major classes of condensed structures. The first of which are known as partially condensed structures, where the CH bonds are not drawn. That saves you a lot of headache. You don't have to draw the CH bonds. The number of CH bonds to reach an octet is implied. Okay? In formal condensed structures, all CH and CC single bonds are not drawn. Only the single bonds. You still draw the double and triple bonds, as well as all other. Additionally, all other double bonds, such as carbon-oxygen double bonds, are not drawn. You only draw carbon-carbon double bonds and triple bonds. So for example, we take the following connectivity of atoms, and in each step along the chain, we write the formula for that functional motif, for that region of our molecule. So moving from left to right, what's the first thing that we see on the left? CH3, so we write a CH3. What's attached to that CH3? CH2. Lo and behold, we have a CH2. What is attached to that CH2? CH, okay? And there are two methods of representing what's known as branching. Do you notice how the chain goes off in two different directions? It's branched. There are two ways of doing this. You can either explicitly show the branched bond. That's option number one. So what's attached to this CH as a branching group? CH3. And finally, what's also attached to this CH? CH3, right? So another way of representing branching is by noting that attached to this CH are 1, 2 CH3 groups. So we can say we have 2 CH3 groups attached. So we can use subscript notation to indicate the number of each functional motif attached to that carbon. Does that make sense to everyone? Now, condensed structures will clearly indicate functional groups in a molecule. And a functional group is a specific group of atoms with a unique reactivity. And if you understand and recognize functional groups, you can quickly draw Lewis structures. So let's talk about the really boring ones first. Alkanes have a carbon-carbon single bond. So for example, the CH3 functional group is an alkane. It just has a carbon-carbon single bond. So the CH3 group is attached to our carbon. So we have an alkyl group or an alkane. Alkenes have a carbon-carbon double bond. For example, that found in ethylene. And alkynes have a carbon-carbon triple bond, such as that found in acetylene. Does that make sense to everyone? One way I like to remember this is the farther through the alphabet you go, the farther you reach the end of the alphabet, the more bonds you have between the carbons as a heuristic. Ein, een, ein, you're going farther down the alphabet, more bonds between carbon atoms. There's one other functional group that's related to an alkene, but has substantially unique properties and reactivity. We call these Airings. They are represented as alternating single and double carbon-carbon bonds in a 6-membered ring. So this is known as an aryl functional group. Often also represented like so, or more canonically with a circle in the middle to represent resonance delocalization. So these are the really boring functional groups. They're important for sure. Alkenes and alkynes are a huge portion of the latter half of this class. Let's now get to a comprehensive table of all the functional groups you should be familiar with in this class. And I would highly suggest, you won't actively memorize it, but I'd suggest practicing drawing structures enough where you can recognize these functional groups quickly. Does that make sense? So in organic chemistry, you're not explicitly trying to memorize. You memorize via practice, and you understand how things work rather than taking things at face value and just memorizing each. Okay, so in this table, I've arranged it where we have the structural formula, the condensed formula, the name ending, and the oxidation number. This is one table that I would recommend printing out and just having by your note sets as we go through later chapters. I'm not going to go through each of these in detail, but I'll touch on the highlights. So cycloalkane, cyclic, so we have our carbon atoms connected in a ring. Halides, so the word halide includes all potential halogens such as chlorine, bromine, iodine, and fluorine. So anytime you have a carbon halogen bond, you're dealing with a halide. Amine functional groups are denoted by the presence of an NH2. Thiols, as their name implies, are denoted by sulfur atoms, more specifically, the SH functionality. Alcohols were covered in Chem 101. They are composed of the OH functionality. Was that covered in 101 or 102, organic structures? It's okay. This is why we're reviewing. Some of these are new, but the alcohol was definitely covered in 101. But the main feature, we have an OH functionality. And ether consists of an ROR functionality. So we have an oxygen atom between two carbons. For the biologists out there, we have the monophosphate, which is the OPO3 2- functionality. And of course, there can be di and triphosphates, such as in ADP and ADP. That's why ADP and ATP are named as such. ADP, diphosphate, ATP, triphosphate, just as an aside. Monophosphates, so we have this PO3 attached to an oxygen atom. The other functional groups that are a little bit more meaty, we're starting to move towards more highly oxidized functional groups. We have more carbon electronegative atom bonds. So the carbon is more electron deficient. There's less electron density on our central carbon. Examples of this are aldehydes, imines, ketones, carboxylic acids, and esters. So these functional groups, and the reason why I talk about them in the same breath, is they are all part of a superclass known as the keto functional groups. So keto derived from the word ketone functionality. So all of these functional groups are ketone derivatives. Okay. Other important functional groups for next chapter are the carboxylic acids and amides. We've already seen the carboxylic acid in what structure? Where have we seen a carboxylic acid before? Acetic acid, exactly. And it's the CO2H with this exact bonding arrangement. I'll leave the rest for you to look over at home. I would not try to hard memorize those functional groups. Instead, I would try to get used to utilizing the idea of functional groups in writing Lewis structures. So if you recognize a functional group, write it out, and that will save you time when you process a condensed structure. It appears we're out of time for today. So we'll meet again in lab in approximately 8 minutes, and you'll take the second quiz in lab.